Alright, good afternoon. With Team MasterMinds, series design projects called Material Selection Mechanism. Advisor is Dr. Benjamin Mizzi. Approaching a current problem that our company is having today gave us the opportunity to develop our senior design project. The company is called Vinyl Corp. They manufacture beads, trims, control joints, and different drywall products. Basically, you have to come up with a design in which will aid a current recycling process, and it consisted of sorting out material residue by size and type, as you see here, the different sizes. The challenges we face is all the material buildup, as you see here, that cannot be reused due to contamination with the ground impurities, and all these boxes currently are being transported by hand. The main objective of the project was to maximize the space facility, reduce the material contamination and the energy usage, as well as the physical labor. Here's a short video as you see the knockouts finally drove through here. The motivation for this project were to design a mechanism that required accuracy, taking into account all the safety requirements, create a system that would improve the career on-the-going process, gain professional experience by interacting with engineers, and introduce a new product to the market. The requirements for the project: durability. We have to consider that this product is going to be used in a heavy industry, so it has to be in some way shock resistant, be able to move it without breaking it. Functionality. Some way it had to be automatic, since we're using air as a medium of conveyance. So once the press cell starts, the air should start in order to reduce the energy usage and the consumption of air. Sizing. This component basically had to fit within the press cell of the mill due to the sensor curtains. And overall, the overall system needs to be easy to troubleshoot and operator friendly. Here the proposed design is here, the different three setups in which the filter can be positioned, ranging from 5 degrees to 23. Here's the conveyor. It's attached, simulating, this is the actual chute that is in the press right now in the company, containing the pressure regulator, the solenoid valve, and the air conveyor at the bottom. Major components for this project were the air compressor, air conveyor, pressure regulator, the drum filter, solenoid valve, sprockets, frame, bearings, galvanized steel boot, and several reducers. Basically, the project is divided into 3 stages. Consists of the material collection, material transfer and flow control, and material sorting. Stage 1, which is basically the collection receptacle. We contain and gather all the pieces from the punch die, allowing them to move freely to the next stage, which is the conveyor. Here's the conveyor and the solenoid valve. Basically, the conveyor will create a vacuum and push on the pellets. Sending them to the filter, and the solenoid valve will be connected to the press cell, in which once the press starts, the air starts flowing, and then if some reason it stops, we should stop the flow of air. Here's the drum filter. It contains 2 inner measures in order to sort out the big particles from the small ones. Also, we can rotate that mesh to create the stent in which we want to filter the particles. This is the final setup picture here. Flow conveyor in the back, the hose, and it would go through here, and then the particles would come, big particles through here, and small particles through this opening right here. It's a short video for the test we did. That's Magdi doing all the pieces. It's one. And Mike just left. Was rotating the drum. That was the transport action. Now you will see in detail the filter reaction. See the big pellets just coming out through here. You can not really see the small ones that fall out through the back. You can see it. The small pieces there. For the manufacturing, we had to, in the drum filter, we got 2 perforated sheets have to roll them, seam them, and weld the flanges to it. For the frame, cut all the steel bars, drill holes, put the bolts, hinges, the sprockets. We have to modify one of the bores in order to fit the bearings we got, and also for those bars where the sprockets are placed in. SolidWorks design showing the filter, the frame, sprockets, and this is the biggest opening in which the mesh can be set up. It's 0.75 inches. The equipment we used, the manufacturing facility was drill press, grinding wheel, bandsaw, rolling machine, stick-on machine. AD and OC helped us with that, and the hydraulic press. Mr. Dr. Schiller already helped us with that also.
As far as for the engineering analysis, we did flow analysis on the chute right here. So it is determined that we made a few assumptions, and it was that the pieces will fall into a free fall, and we calculated the velocity right here at the entrance, at the exit of the chute, and at the entrance of the air conveyor. Based on Bernoulli's equation, our main concern was to find out how much pressure we were going to need at the air conveyor so the pieces wouldn't fall, wouldn't fly all over the place. And we assumed a range of velocities at the three different positions, 5, 14, and 23-degree angle for our setup. And we assume a range of velocities ranging from 2 to 10 inches per second. And based on this assumption, roughly around 15 psi for each setup was determined to put it to as an inlet pressure at the air conveyor.
We did the stress and displacement analysis for 3 critical parts of our design, which is the top of the filter, that the drum filter is located, top of the frame. We did the stress analysis for the biggest sprocket, which is the big filter is rely on that, and the plate that the 2 sprocket is placed on. These are the force distribution at the fixture for the top of the frame. We have 2 components of the force, vertical and horizontal. We find all of those components, and by knowing the 2 degrees, 2 angles, which is the 5 degree and 23 degree, which is the maximum angle that we have, we do the displacement convergence. And at the optimal mesh, the factor of safety come for the 5 degree, 12.75. And for the 23 degree, for the top of the frame, the factor of safety is 12.9. We did the stress and displacement analysis for the plate that the 2 sprocket is located on. And we have, in a larger sprocket, we have the additional force because the drum filter is relying on that sprocket. And we find the forces that is applied to that sprocket. And these are the fixture and the force that applied. And we also did for 2 angle, which is the 5 degree and 23 degree, which is our maximum angle that filter is located. And after finding the optimal mesh, after the convergence study, the factor of safety for the 5 degree is 17.5, and for the 23 degree is 5.9.
The same analysis that Maggie just mentioned, as far as stress analysis, we practiced that same analysis on the sprocket assembly. And again, we broke down the total weight of the filter into the X and Y components to determine the forces. And we found the stress displacement convergence on the sprocket assembly at the 5 degree angle, and we found a factor of safety of 2,000 for this setup. And at the 23 degree angle, we found a factor of safety of 462. And this is at the rods that connect the filter to the sprocket, which are the weakest ones of this assembly. And we did the same analysis in the fasteners and the hinges, since they were the weakest part of our assembly. And we assumed the whole weight of the filter, which is 50 pounds, on one single bolt. And same for the hinges. And the factors of safety for the bolt is 1.33, and the hinges is over 20. So, and this is how we did the stress analysis on the bolts. We fixed it at the head, and then we put the load in the tip of the bolt. This is the worst case scenario on one single bolt. And we did the same thing for the hinges, and like I mentioned, 20 for factor of safety. Another analysis that we had to do was we had to determine a working RPM for a filter so the pieces could be accurately filtered. So we assume RPM, working RPMs for the filter between 6 and between 6 and 30 RPM. We found the mass moment of inertia for the whole filter, and we determined a 1 to 5 gear ratio for this setup. Why a 1 to 5 gear ratio? That is the biggest sprocket that comes closer to the diameter of our whole filter, and that is the smallest driver gear that we could find in the same catalog for this particular purpose. And we found the torque required to rotate that filter at each given RPM to find the power required, again, to turn it at each RPM. At this point, we were in a theoretical analysis. We didn't know exactly how much RPM was going to be necessary to filter the pieces. As you can see here, we can see the linear relationship between RPM on the driver and in the gear, as well as torque. Next one. And this is the graph that we were really interested in, which was how much power we were going to need from a motor to rotate that filter at certain RPM, and this is the relationship that we found. And we found a working range. We knew that we were in between 6 and 12 RPM for that filter, and we did some interpolation based on our given horsepower for the motor. If we go to each catalog, we can find that the motors come in certain increments. So our best bet was between 1 and 1.5 horsepower for the motor at the driver.
The cost that was estimated was 1,500, and the final cost for this project comes up 1,374.6. And these are include the expensive parts. The most expensive one is the drum filter that we have, and the air conveyor in a transporting part. The hours that we spent is 195. That is include design, manufacturing, and the testing parts. The sorting and filtering mechanism exists around the world, which is the metal separator in Europe, or plastic waste recycle machinery in Asia. Also, the transporting mechanism exists like a vacuum material transfer or auger to send the material from one point, the specific point, to the points that is requirement with different heights. And our system is combined of the transport mechanism and the filtering and separating mechanism. We believe that by modifying or implement our filter, we can aid some of the issue around the world, like water pollution. The two industry that this kind of filter can work is the food industry and the recycling industries. These are our timeline, and fortunately, we can reach and approach all of the due dates, and this is our final setup.
Okay, for future improvement, we consider, how to improve the current project will be using a hydraulic mechanism to raise and adjust the angle of the filter. Incorporate maybe smaller drums within it to further filter the pieces. Incorporate the wide valve, which will distribute the parts into interior and exterior. We didn't implement it here, mainly due to budget, and also we just needed to show one side of the thing, and that the filter was actually working and sorting out the pieces by size, which is the major component. Also to optimize the rotational speed. Here you see the wide valve, how it worked, which we did, what type of material they're running. To conclude, we managed to reduce the material contamination, reduce the energy usage, improve the material transportation method, perform the product categorization, and introduce a new prototype for worldwide use. It's a short video of the outcome of our project. Volume?
Volume, yeah. Be nice to hear it.
there a crest run on there?
Alright, it makes around 20. No.
How
There we
many
go.
engineers does
How
it
many
take?
monkeys? Yeah, exactly. So, good sound. They're all up. Come on.
Is there a crest run up there? No, at the console. At the console, is there a crest run there?
I don't know, yeah.
What happens after
There we go.
extrusion is it goes through a water bath and a puller.
Restart.
And then into a secondary process where it punch holes in the member. These holes we call punch outs. Port manufactures a variety of rigid PVC parts. Most of them are for stucco and drywall applications. And when they're extruded out of rigid PVC, they come out as a solid shape.
Thanks, Eric.
What happens after the extrusion is it goes through a water bath and a puller, and then into a secondary process where we punch holes in the member. These holes we call punch outs are a problem that we have today. You'll see a variety of shapes when our drywall products are very small and our stucco products are very large. And all these punch outs have to be diverted back into the product. Currently, they're collected through an air-driven system that are collected into gaylords and then recycled into new parts. Our process is not efficient because the air constantly flows at full pressure, and the parts often end up on the ground because of an inadequate collection system. So when the FIU team came and asked for a problem that we have, we asked them to find a solution to convey these products from the punch process back into the gaylord so they can be reused and reduce the amount of air consumption as well as reduce the amount of particles that fill the floor. So the solution that the FIU team came up with was an air conveyor that reduced the amount of pressure and flow that was required to drive these parts from the punch machine into the collection boxes. The process will significantly reduce the amount of air consumption as well as contain all of the punch outs in the chute that they designed. This will be a huge savings both in terms of energy as well as in terms of manpower cleaning up the mess of punch outs and improve our safety of our plant overall.
Any question?
Okay, so listening to what he said, what he was most excited about was your air conveyor. But I see the biggest part of your project was the filtration system.
Yeah, they're still considering if implement this part, because right now, I mean, they're going through several mixes to find the ideal material when running the product. So there's like a ton of different types of material, not only interior, but now they added color, not colored. So I mean, the filter itself would only function for interior or exterior, not for the color type. So we need to still figure it out how to manage that by implementing more filters or different guidelines where the product needs to go, I guess.
Okay, the other questions I had is how do you ensure that other materials don't get into the supply line, like metal particles or other things like that?
From the actual punching die in
Yeah.
the knockout. Well, they have now in the actual mills, they have metal separators.
Magnetics.
Yeah, magnetic separators where they pick up all the shavings from the punching die when it hits the part that is going down. So we didn't have to implement that in the
Okay.
design.
And why is it so critical to have separation of the particle size?
Because the big parts, they cannot be reused back. I mean, they cannot put it as it is to the extruder. They need to first grind it. That's what they do now. They grind it first so they can be easily transferred to the extruder and then just into the final product. that they
So
use.
why don't they just grind it all?
The small ones, they use it as it is. They mean it saves time and labor by having the guy go to the grinder and dump all the pieces there. The smaller they use as it is, and the big ones they have to regrind.
Okay, my last question is, I know you specifically said that what drove your sprocket size was the diameter of your filter. Why is it so large? Why did it have to be that large?
The filter or
The
Yeah,
sprocket,
the
the
filter.
sprocket. The
Oh,
way-
the filter.
Why does the filter have to be so large,
Oh.
which forced you to go to that size sprocket size?
When we were thinking about the design process, the main constraint that we had was manufacturing this filter. We had a really hard time trying to manufacture this filter because of the rolling of these metal sheets. So we found that a company that actually had the actual equipment to do this could only do it in this size as a maximum
Gotcha, so
size.
it was a manufacturing restriction.
It was a manufacturing issue, exactly. So if you want to put this in a bigger scale, you can, if you have the equipment, you can make the filter as big as you want. So, and that is what drove this sprocket size, basically.
Okay, thank you.
All right, you showed 195 hours of labor. I guess that's for your entire manufacturing process, design, analysis, manufacturing process, correct? How was that divided up amongst the three of you?
We have the table that we separate who do the design, who do the manufacture more, and who work in the theoretical parts. And each
Okay.
one is by the hours.
All right, got it. I guess I missed that. Okay. I got 195. I didn't see the distribution. Thank you. All right, any other questions?
Sure, I can. So in your actual test, what was the distribution of the materials? Was it 100% big in the one box and 100% small in the other one, or did you?
I mean, some of the parts was due to the accuracy of the filter itself. I mean, the manufacturing, Camille was saying, wasn't that precise due to cost. I mean, we could have gone to ranging manufacturing $1,000 the first that we did. It ended up being 600. So that, I mean, it was like 80% of the pieces were falling in place in each box. I would say that.
Our tolerances for the filter wasn't that accurate because of manufacturing issues.
Yeah, I remember you saying.
And if you go to better quality materials and higher tolerances, you're gonna get a more accurate result for the filtering process.
That's it? All right, thanks so much.